Hey everybody, it's Warner, and this is the extra free response or FRQ for dynamics. And this is a little bit of practice, so hopefully this will help you. We have a horizontal Atwoods machine, which means that we have one thing that's horizontal and the other one is vertical. We do know that this thing is going to accelerate to the ground. So this box accelerates to the ground, but because it's tied to the pulley, and then the pulley changes the string, comes over here, we know that this will accelerate in this direction. So we're going to put plus A. Let's also define these as the positive x direction, and we're going to do that based on what we have in terms of right here. So we're just going to say that this continues in the x direction even though it's technically in the y. And the only reason we do that is because if I don't have the pulley, then that means that this string would have to go to the right, and that would be the x direction. Where it says block M2, we really need to move that title over here. And they want us to draw a free body diagram for both of these. So we want to do it for the block on the desk and the one that's hanging. So let's do the hanging one first, it's easier. So I'm going to go all the way down to the bottom. We're going to say that this is one vector. Now we've got another one pointing straight back up. Over on this side, I've got straight down, and I have straight up, but I also have to see that I do have going to the right, there is tension, and then going to the left, there is friction, but I'm going to make that one shorter, and then we're going to talk about why. Let's go back and label all of these. This is the normal force. This is M1G, this is M2G, this is FT, because that's tension, this is also tension, and then this is our force of friction. Now why is our force of friction smaller than our force of tension? Why is this longer than this one? Well, because it's accelerating, and it's accelerating in that direction. The other thing that we need to do is we're going to go back and we're going to make this force of tension a little bit shorter. So if we do that, we're going to make them both a little bit shorter. And the reason we're doing that is because it is moving and accelerating to the right. So I'm going to make this one go here, and then this one, I probably need to make it a little bit shorter. Oops, so I didn't grab the right thing. So I'm going to make it a little bit shorter here. And let's just go over and let's make it go to right here, so that'll be better. So now this one is only 4 long, this one is 2 long, and that's my force of friction. And then I have M2G is bigger than FT, so this one's a little more complicated than what we were doing before. Okay, now that we've done that, they want us to derive an equation for the coefficient of friction, mu, in terms of M1, M2, G, and the acceleration of the system. So let's remember the force of friction, which is on your equation sheet, is equal to mu times the normal force. Well, we have the normal force here. We know the force of friction, so we can find mu pretty easily, but you can't just solve for mu here. We have to do it in terms of M1, M2, G, and the acceleration of the system. So that means that we've got to do a sum of the forces equation. Let's do a sum of the forces equation in the x direction, and that means that it's the total mass because both of these masses are accelerating, and we're going to multiply that times the acceleration. Let's do each picture one at a time. This is in the positive direction, so notice pointing down is positive, so this is M2G minus FT plus, and then remember we go here, we don't go up and down, we're going to go left and right with this one, plus FT minus the force of friction, and that is equal to M1 plus M2 all times the acceleration. Now that we've done that, let's show what the force of friction is. So we're going to put M2G minus FT, minus FT plus FT. Oh, good. So that's minus the force of friction, but we said that the force of friction is mu times Fn. So we can leave it like that, and it's equal to M1 plus M2 times A. Now, I know some of you might say, oh, but Fn is equal to M1G. Can I put that in there? You can, but the math gets really weird. So I would encourage you to leave it out. Here, we'll put it back in, but we're going to wait till we're completely done, because we can't have Fn in there. You'll see that it says to do it in terms of M1, M2G, and A, and any constants. So that constant is G. So let's solve this for U. We want to solve it for mu. If I take and add mu Fn to each side, the thing I'm going to need to do is subtract this from both sides, but that kind of looks a little weird. So let's just subtract M2G. So we're going to have negative mu times Fn is equal to M1 plus M2 times A minus M2G. Now I'm going to get rid of the negatives by making multiply everything by a negative. So I get mu times Fn is equal to, now this becomes positive, this becomes negative, so it's M2G minus M1 plus M2, and that's all times A. And if I want to get the mu all by itself, I'm going to do mu is equal to M2G minus M1 plus M2 times A, and I'm going to divide that by Fn. But I'm not done, because it says you can only have M1, M2, G, and A in it. The U stays here, mu stays here, but over on this side I've got Fn on the bottom, so I got to get rid of that. So now mu is equal to M2G minus, and then this is M1A minus, because it's negative here, that's minus M2A, divided by, so on the bottom, Fn, remember, is equal to M1G. Why is that? Because the sum of the forces in the y are equal to 0, because it's not accelerating up and down. And so it's not doing anything this way, it's only going this way and accelerating to the right. So this is Fn on the top minus M1G on the bottom is equal to 0. So Fn is equal to M1G. So now I'm good. So this Fn becomes M1G. And you'll notice that I can't cross anything off. I can't cross this M1 off, because then I'd have M2 over M1 here and M2. So I'm just going to leave it just like it is. And that would be your answer, because all it does is want an equation. In the next part of this, what it would like for you to do is, what is the value of the coefficient of friction necessary to produce an acceleration at 2? So really all we're doing here is taking the equation we just made and we're plugging it in. If your equation was wrong, that's okay, because when you well, it isn't in the fact that you're going to miss a point, but if you use the same wrong equation here and you solve, you will get points for that, and full points. So we're going to find mu. That's equal to M2G. So M2 is 5, multiply times 10, minus M1. Oops, I don't want that, so we can just get rid of this. So M1 is 4 times the acceleration, which is 2. And then minus M2, which is 5, times the acceleration, which is 2. So I didn't really probably have to factor that out. I could have just left it, but I went ahead and did that anyway. And I need to divide all of that by M1G. So M1 is 4 times 10. So now I can do my math. I'm going to use my calculator over here. So I've got Desmos set up. So I've got 50. And so I got to turn my numlock here. So this would be 50. And then I'm going to subtract 4 times 2 is 8 minus 10. And I get an answer, and that answer is 32. And I'm going to take 32 divided by 40. Oops. So I'm going to take 32, and I still don't have my numlock on. 32, there we go, divided by 40, and that gives me 0.8. Remember, mu values should be in between 0 and 1. That's the typical ones that you get. And so this is 0.8. And there's no unit. Remember, there's no unit for this. How do we know that? This is a Newton, this is a Newton, that's a Newton, and this is a Newton. And a Newton divided by a Newton is no units. So we just leave it. And that is letter C, and that is the end of the problem.